So in these videos, we keep talking about standards, right? Standard 1, Standard 2, Standard 3. I've got to make the standards. I know the concentration of them. And that's what we use to make our calibration curves. So the concentration is known. That's the whole purpose. It relates the concentration to the signal of the instrument that I am using. So that way I know when I run samples how that concentration, how that signal relates to the concentration. Well, there's a proper way to make standards in a laboratory. And some people get confused with this because they're told different ways when they go into a laboratory. And I'm going to tell you the preferred method of making standards. Don't use a cheater shortcut. Right? We don't like shortcuts in a lab, and there's a reason that we don't like this shortcut, and I'm going to explain it to you. So when we make standards, sometimes we start off with a primary standard. So for instance, we are using a 1,000 part per million fluoride concentration. This is something that was ordered. It's something that was shipped to our lab. It's something that's certified, and it says, yes, we tested it. It is 1,000 ppm. You can feel good about it. Now go use it. So this is our primary standard. And with this primary standard, let's say that this 1,000 is way too weak. So we want to make a standard of a 1, a 2, a 3, and a 4 part per million concentrations. Well, if I do the dilution here, I can take my 1,000 ppm. I don't really know how much of that to use. I want to make a 1 part per million, and let's say I want to make 100 mils of it. All right, so I'm going to bring up the calculator for you folks just so you can walk through the math with me. We need to solve for x using the dilution equation. So 1 times 100 is 100, right? And then to solve for x, that's 1,000 times x, so we need to divide by 1,000. So we're going to divide by 1,000 here, and we get 0.1. All right, so x is equal to 0.1. Well, keep in mind, this was in mils, and this was in ppm. So therefore, this has to be in mils, and this has to be in ppm. Your units have to stay the same on both sides, right? So this is 0.1 milliliter is what I need to add to this volumetric flask and dilute with my solvent up to the line. Well, sometimes these concentrations are very small. And I'm not comfortable using those small, little bitty couple of drops of standard. So sometimes we take this primary and we do a initial dilution of it. And let's say that I go down to 100 part per million instead, right? So this way I can make this 100 and I don't have to worry about small little tiny volumes to make my standards with, because that's going to actually increase my chances of error. When I use these tiny little drops of stuff, my error can skyrocket because I'm relying on a couple of drops instead of milliliters worth of stuff. Okay, so with that said, no matter which way I do this, right? No matter which way it happens, I can use the 1,000 or the 100 that I've made, and I need to use these two in order to make my series of standards with. Okay, well, here's the proper way to do it. I'm going to use maybe the 1,000 or the 100, depending on which way I deem fit. Maybe I don't want to make 100. Maybe I want to do a 10. Who knows? That's up to you to figure out. But whichever way, you use that one to make the 4, and you use it to make the 3, and you use it to make the 2, and you use it to make the 1. That is the proper way to make standards. So you might be scratching your head right now, and you might be like, well, what else? What other way would there be to do it? And this is something called a serial dilution. Stay away from serial dilutions, people. You don't want to do them. And the reason is because the errors can happen, and you will not be able to pick up the error. Okay. So the proper way is to take an original and use that original to make all of the rest. Now let's talk about serial dilution. So I'm going to erase these. And a serial dilution is slightly modified. So in a serial dilution, S-E-R-I-A-L, some people would take either the 1000 or the 100, whatever the starting thing is that you're using, and they will make the strongest one. Then they will take that strongest one and use it, dilute it, to make the next weakest. And then use that one to make the next weakest. And use that one to make the next weakest. That's called a serial dilution. And you never want to do them. And this is why. Let's say that you made a mistake in your math. And when you figured out your numbers to make the 4 part per million, you miscalculated. So this number 4 was made wrong. Well, if number 4 was made wrong, and if you do a serial dilution, the number 3 would also be made wrong. It's not the right concentration because you used 4 to make it. And then number 2 is going to be wrong because you used that wrong one to make it. And then number 1 is also going to be wrong because you used number 2 to make it. It's a chain reaction that happens. And sometimes you won't be able to pick up on them. And this is why. Because when you go and you run those standards and you messed up on the original and that original was miscalculated, but you used that original to make everything else, and everything else according from that point on was made correctly. Math-wise, it was done correctly. But because that number 4 was wrong, and let's say that it's not really a 4 part per million, but a 40 part per million, you made a mistake. Whoops. But you don't know that. Well, instead of a 3, a 2, and a 1, this is a 30, a 20, and a 10. And when you go and plot those on a calibration curve, guess what, people? They still make a straight line. You will never be able to pick up that mistake. Because this straight line represents the 40, 30, 20, 10. Because really you made a mistake in the calculation when you made your very first one. Now compare that to a non-serial dilution. Let's say that you miscalculated number 4 and you made a 40 instead of a 4. Well, that signal is going to be extremely high, right? It's going to be way up here because that's a super strong concentration compared to all the others. So if you did not do a serial dilution and you use this original and you calculate it to make the 3 and you calculate it to make the 2 and you calculate it to make the 1, then what you could find out is a calibration curve that would look like this. And you would be like, whoa, no, something's wrong, right? The 1, the 2s, and the 3s, they all work out kind of well. And that would be my regression line if they were made. But for some reason, spot number 4 doesn't make any sense. What happened? And then you could go back and take a look at your math and say, oh, I miscalculated. That 4 is not a 4. It's a 40 instead. So I need to go back and I need to make the standard number 4 at 4 part per million and rerun it and put that into my calibration curve. And hopefully it will fit for round number 2. But if you did not do that, and you make a mistake on the first one, and then you use that to dilute all the rest of them down and down and down and down, or use 3 to make 2, use 2 to make 1, that's a serial dilution as well. That's where your problems are going to lie, because the same mistake follows through. And you do not want that to happen. All right? So stay away from serial dilutions. Whenever possible, do not do them. Now, there's some times in a laboratory that you've got to do them, right? And that's where we take something that's very concentrated and we weaken it down and then weaken it down one more time in order to get it to a level that we need. Sometimes there's no way around it. But you better hope and cross your fingers that all of the standards that are prepared in the middle are going to be proper. Because if you're using that to make the rest of your standards with for the calibration curve eventually, if any one of these are incorrect, then we have a problem. And you might not be able to pick up that problem until it's too late. So sometimes we can't get around them. Sometimes we have to do them. And if you're looking at a lab procedure that we've given you and it tells you to do that, there's probably a reason for that. And the reason is you're trying to get to such a low concentration that that's the only way to get there. But if you're making standards for a calibration curve and you vary the concentration up, that's pretty close together, right? I mean, this is pretty far apart. 1,000 to 100 to maybe a 1, right? These are not close. So we have to dilute. But if they're close as far as calibration standards go, 4, 3, 2, 1, never use one to make the other. Always go back to the original that you're pulling from and use that to make all of your standards in the calibration curve. So stay away from serial dilutions, or you might go serial and loco on us in the lab when you figure out you've got to do all your standards all over again.